My name is Andre Barbosa, and I'm from Oregon State University, and also presenting on behalf of Peer. In this first slide, you can already see that there were many people or many groups involved in this work. We have to acknowledge the NSF Rapid Grant, which is CMMI 1545632. The people that are here in orange at Oregon State, and then Andreas Stavridis in blue, were the co-PIs, but in no way did the work limit to only those three people. You see there's a big group, not only in the US, but also in Europe, in Portugal, in Italy, and also at the bottom we had lots of contributions from people in Nepal. One of the key groups, again, is NSET, and let me see, there we go, NSET, and there were four main people there that worked with us very closely through about a month of time that we were in Nepal. For our effort, initially because of the National Science Foundation Rapid, we were focusing on reinforced concrete buildings with masonry infill. The interesting thing for the US is that there are many buildings from the 1920s and 1930s in California, in Seattle, in Portland, that have some, they're non-ductile buildings with masonry infill. And so we're trying to learn there and see what are things that we can bring back to the US. Another key thing was to try to use new technologies for damage assessment. We wanted to quantify our damage measurements, not just qualitative, saying, yes, there's a crack and it's about this big, but we want to know how big they are. But using new techniques and mainly ground-based LiDAR scans, we also used unmanned aerial vehicles, and then we used softwares that allow us to do structure from motion, and I'll show you a few examples here later today, but allows us to go and build 3D reconstructions from 2D photographs. And we also had 360 panoramic cameras. So the objective of using these techniques was not just for the sake of it, it was what can we learn in terms, and how can we do better damage assessment with the new technologies that are out there. And that was the main focus initially, but because the group was a big group and there were a lot of other interests, we ended up also focusing on dynamic identification, so frequencies and mode shapes of reinforced concrete structures. And we classify them in two main types first. One, which would be the non-engineered buildings. Even though they are reinforced concrete infill buildings, there are many buildings that are non-engineered. Non-engineered in Nepal typically means you copy what was done on the building next door, and that ends up being columns 9" by 9" with four number 16 in terms of millimeters, so that's around number 5, number 6 bar in the US. And then beams have drops of 9 inches, slabs of 4 inches. So typically you end up having designs that are weak column strong beam. And there are many buildings in Nepal that have that. And that happens not only in Nepal, it happens in India, in Pakistan, it happens in the region. So it's also useful to learn from those. In Nepal, they have something in between what we classified here as well-designed buildings. And well-designed buildings is following what Brett was saying, is following Indian codes, typically also some Nepali codes, but when it comes to seismic, is mainly Indian codes. The codes themselves are fine. Enforcement is sometimes the problem. The designs are fine, but the enforcement is what sometimes lacks. They do have something in between, which is called mandatory rule of thumb. Okay, and mandatory rule of thumb is better than a non-engineered building. It typically is going to have 12" by 12" columns. It does have a code, so ties and spacings and all of those things are, by mandatory rule of thumb, well prescribed. Then they're not necessarily well built in the field because they end up copying what somebody else did next door. So, but there is this mandatory rule of thumb, and I was saying columns are 12 by 12 inches. The drops in the beams are now 12 inches, but they typically have 4-inch slabs. So again, even though it is a mandatory rule of thumb, you do end up having something which is very close to, again, to a weak column, strong beam. So that's one of the things that they've identified, and they had identified, and their mandatory rule of thumb is going to be updated to have stronger columns. And they're talking about 16 by 16 columns, and the beams will remain the same size. Then, again, well-designed buildings are typically well-designed, and I'll show you examples of those here. That's going to be the focus. We also ended up doing damage assessment at a larger scale, using typically ATC 20 type approach, but also EMS 98, which is based off Europe, for urban and rural areas. And what we're trying to do is how much of these assessments can we do reliably using unmanned aerial systems or vehicles, and how much do we still need to teach our systems and learn. So that's something that's going to be coming back. And because we were working so closely with NSET, it was just natural to help them with some of their assessments that they had to do. And so we did a few buildings of that. In terms of the extent that we covered, we've already heard today about the epicenter of the, and actually that's 12th May, that's wrong, that should be on the left, the 25th of April. And then on the right in red is the main shock, sorry, the aftershock of 12th May. We did have initially also some GPS trackers, but I thought we went all over the place, so I thought it would just be easier to pinpoint some of the towns. And we did cover a wide range. The box in gray is where we spent most of our time. We went further west near Gorkha to Manakamana just on one of the days, but we spent essentially a month in this box in gray. We did the whole team, and again, it's a very big team. We did many, many buildings, and here I'm just listing for the RC structures with infills. I'm listing buildings that we did detailed assessment on, and on some of them, I have here, it's on 15 buildings we did ambient vibration testing on, and including one of them, a temple, so not on the RC structures, but we did do a temple in Bhaktapur. We did 2 historic centers that is looking at urban scale vulnerability, and there what we're trying to come up with is what we call damage probability matrices, so conditional on the shaking, what's the uncertainty in terms of damage. Similar buildings, one is failing, the other one isn't, so we're trying to characterize that probability of damage. We looked at the urban rural scale area. I've listed here the towns, including Piskar, which is a village. It's in Sindhupalchuk. We have to drive to a town. The closest town is Barabise, which is a 4-hour drive. And then it took us about 4 hours to do 15 kilometers on these narrow roads, and sometimes we had to get off and walk to get up there. And we spent there 2 days just trying to get a feel of what these villages had really seen in terms of damage. And it was disastrous. So about 95% of the buildings completely collapsed. So it's a long list of buildings. We did look at 3 historical unreinforced masonry structures, and those were actually by request of NSET, so trying to provide them some information. And because our team did include some geotechnical engineers, we also have some data on landslides and liquefaction that we'd like to share eventually. Within a year, we'll be sharing this data. The type of assessments went from ATC 20 rapid evaluations. We have about 400 and something of those that we filled out. And then all the way down to some non-destructive testing, trying to characterize the reinforced concrete structures, laser scanning, and unmanned aerial vehicle data. For some of you that don't know what laser scanning is, I did not know much about it even before we started this project. Not really. I have a student that's been working on it for 2 years, but before 2 years ago, I didn't know much about it. It's really a light detection and ranging technique, and it's used to determine the surfaces, geometries of the structure. So essentially, you have a source, it shoots a laser in many directions, and then it creates a point cloud. And this point cloud is, and you see from there, for example, if you're shooting at this circle here, you would only see part of the circle because that's where the laser is shooting from. But if you do it from many, many positions, you can do things like this. You can actually develop AutoCAD drawings for your structure. So it's another tool that you can use for geomatics. And what we were particularly interested in is you can do things like this. This is a wall in actually the school that Brett showed us in Sanku. He was showing the column over there from the outside. This is on the inside of that building, and we see that the infills are cracked, and on the back there was actually a column that had failed in shear. So we can quantify and we can measure sizes of cracks. We have a scale that we can go in after the fact, after we've done the laser scanning, and continue to have this data to go back and learn more from what we've collected. In terms of unmanned aerial vehicles, there's many advantages, and they're in the news very often. They were also in the news in Nepal because 2-3 days later, after the main shock, there were drones flying over the temples, and then they banned their use. We were lucky enough to be able to fly on 2 sites because we requested the local community, and they said, I'm the one that says what goes on in my town, and you can. And so that's how we did it. And then I'll show you some later. So for this talk, because we have a lot of information, I can't go over it all. I'm going to show example of 1 tall building and then 2 school buildings, because it does show some of the things I've talked about. And then we will be coming up with several publications. Right now we have a full list that you can look at. It's here at the bottom, a list of the structures, and we're actually keeping track of where we're at in terms of the data processing, because it is a lot of data to process. In Hatiban, we've heard about Hatiban today already, but in Hatiban, so it's near one of the edge basins, or basin edge effects, there were these 4 buildings, and these 4 buildings had different heights, 4 towers. The 2 towers at the end had about 18 stories, and the 2 towers in the middle had 12 stories. Okay? If you remember the response spectra, I don't have it here, but if you remember the response spectra that Yusuf showed, you'll see that there was that unusual peak at 5 seconds, right? So the taller the building, the more damage it would see. These buildings, and that's what happened. The T1 and T4 are 18-story towers. They saw substantial non-structural damage and some structural damage too. And the 2 shorter towers, T2, T3, had very, very, very little non-structural damage. Okay, so that was interesting. It's things that we know. It's in the textbooks, but actually see it in the same site. It was very interesting. So we were particularly interested in this building, so we did laser scanning or LiDAR on all of the 4 buildings on the outside, and we did detailed laser scanning on 3rd story, 6th story, 9th story, 12, 15th story, so forth, so we can have an evolution of the damage. And we collected data on this. We also, in summary, after what we had seen, and I have a few more pictures just to show, but we saw that these buildings were designed for these shaking intensities. They actually did a good job in the construction. In terms of what the buildings are designed for, if you think of life safety, and that's even what our codes today are telling us to design for, the buildings performed well. The buildings are repairable, but there's significant losses. They're going to take about 1.5 to 2 years to make all of these repairs. And right now, they are discussing with insurance companies, because they were insured from the construction phase of how they're going to work. One big thing that came up is a big misinformation from the media. And this big misinformation comes about because when people look at big cracks in masonry infill, they really get scared and they think the structure is going to fall. But even though the structural part was not very damaged, except at the base, but still it looks worse than actually was, because this is work that we were doing in terms of our detail assessment. We were taking out the we wanted to see the concrete structure, and so we had to chip away just to get to the concrete. Some other examples of things that we saw. We did see in some local areas, and this, maybe you can't see it here, maybe online you'll be able to see it, but there's cracks into the beam column joints. And in several places, these cracks, not only the beam column joints, in the beams, there were substantial cracks in the slabs, but these slabs are typically 6 inches thick, not the at least 8 inches that we have. We did ambient vibration testing. This is just our setup, a portable setup, and an example of some of the data that we collected. On one of the towers, we had one setup where we had 10 accelerometers, and processing and collection of the data. This is very preliminary results. We can see that we were able to identify the main periods of the structure. So we did that using the system for many buildings. A group from Porto, they brought in seismometers. So we also have on 2 other towers, we have seismometers, and they did about 10 buildings using seismometers to also get ambient vibration data. And they had an interesting idea, which is to also, for modeling purposes, if you want to account for the infills, we never really know what should we do in terms of the parameters for our modeling. And so they are doing sensing of the walls, and they have some interesting results we'd like to share soon. Site characterization was important, so we teamed up with a couple of people from GEAR that were there on the field, and they did some microtremor, essentially to try to come up. This is in one of the buildings that Brett showed, to try to come up with the shear wave velocities and if there are topographic effects that we can account for. Very briefly, I am running out of time, or I'm 1 minute over time. The school buildings, we looked at school buildings, and this is an example of a school building that represents and mimics many things that are done in Nepal. Initially, they built 2 stories, and after they had the 2 stories, the 3rd story was added on. So the 2 bottom stories had the 12-inch by 12-inch columns I was telling you about. When they added the extension, they moved up to a 12 by 9-inch. And the other thing they did was they wanted to have a big hall. So instead of in the bottom stories, they have lots of infill walls going across. In the top story, they don't have those walls because they had a bigger hall. And so all the damage was on the 3rd story. So vertical irregularity, and we saw substantial damage. So there were other schools. I'll just jump to this one, which is at in Bungmati. We did this damage assessment at the urban scale using UAVs. And I'll leave this video as, it's actually not showing there, but it's showing there. So this was based on 1,600 pictures taken on a drone. And then using structure for motion, we can build the 3D representation of the town. And there was lots of damage in this town, as we start seeing as we zoom in. The blues and yellows are tarps that they put on the building so that they don't get flooded in. And what we're doing now is we're using these techniques. We also did on the field visual assessments, but we're using these techniques to try to calibrate and see how much we can do based on the drone alone. I'll pass on to Judy. We did also we have data on hospitals, but I'll let Judy talk more about hospitals. Thank you.